The date was July 23rd, 1944, and Technical Sergeant Raymond Briggs stood in a maintenance depot outside Saint-Lô, France, staring at a problem that shouldn't exist. The M4A1 Sherman tank in front of him mounted the new 76mm high-velocity gun, the weapon that was supposed to finally give American armor a fighting chance against German Panthers and Tigers. On paper, the 76 could penetrate 4 inches of face-hardened armor at 500 yards. In practice, after 2 weeks of combat in the Normandy hedgerows, crews were reporting something different. The gun was underperforming, catastrophically. Rounds that should punch through Panther glacis plates at 400 yards were bouncing off at 300. Shots that technical manuals promised would disable Tigers were leaving scratch marks on their armor, and very angry German tank commanders who proceeded to return fire with guns that never seemed to miss. American tank crews dying because the mathematics didn't match reality, and nobody in the chain of command wanted to admit that the Army's solution to the German armor problem wasn't working. Briggs wasn't supposed to solve this. He was a maintenance welder, a former pipe fitter from Gary, Indiana, whose job involved repairing broken track links and patching holes in armor plate. He wasn't a ballistics engineer or an ordnance specialist. He had a high school education, 3 years of trade school, and 6 months of combat experience that taught him one critical lesson. When the technical manual says something that gets soldiers killed, the technical manual is wrong. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The M4 Sherman earned its reputation as the workhorse of American armor through sheer numbers and mechanical reliability. From 1942 through 1945, American factories produced approximately 49,000 Shermans in various configurations. It could be manufactured faster, repaired easier, and shipped more efficiently than any comparable tank in the world. What it couldn't do, at least not with its original 75mm gun, was reliably kill German heavy tanks. By the summer of 1944, this had become a crisis. The Sherman's 75mm M3 gun could penetrate roughly 2.5 inches of armor at 500 yards using standard M72 armor-piercing ammunition. That was adequate against German Panzer IIIs and IVs, the tanks that dominated North Africa and early European campaigns. But the Panthers and Tigers fielded in Normandy had frontal armor ranging from 3.5 to 7 inches thick, angled to maximize effective thickness. American crews were engaging targets they couldn't kill while taking fire from guns that could penetrate a Sherman's armor from twice the distance. The mathematical result was predictable and horrific. 1st Armored Division after-action reports from June 1944 documented exchange ratios approaching 4-to-1. For every German heavy tank destroyed, the Americans lost 4 Shermans. In some engagements, the ratio climbed to 6-to-1. The Army Ordnance Department knew this was coming. They'd seen intelligence reports about German heavy armor development as early as 1942. The response was the 76mm M1 gun, a high-velocity weapon that fired a heavier projectile at higher velocities. The M1 could theoretically penetrate 4.2 inches of armor at 500 yards, enough to threaten Panthers and give Tigers something to worry about. Production began in early 1944, and the first M4A176 tanks reached Europe in July. The crews loved having a bigger gun right up until they fired it in combat and watched their rounds bounce off targets that shouldn't be survivable. The problem wasn't the gun itself. The M1 was mechanically sound, well manufactured, and performed to specifications during testing at Aberdeen Proving Ground. The problem was the ammunition, specifically the propellant charge, and how it interacted with the gun tube under combat conditions. American 76mm armor-piercing ammunition used a projectile weighing 15 pounds, launched by a propellant charge, generating approximately 42,000 pounds per square inch of chamber pressure. That pressure accelerated the projectile to 2,600 feet per second at the muzzle. Physics dictated that penetration capability depended on projectile mass, velocity, and the material properties of both the penetrator and the target armor. German Krupp cemented armor used a face-hardening process that created an extremely hard outer layer backed by tougher, more ductile steel underneath. The hard face would shatter inferior projectiles, while the backing layer prevented brittle fracturing of the plate itself. American armor-piercing shot used a homogeneous steel alloy hardened throughout, designed to defeat this combination through superior material properties and kinetic energy. The theory was elegant. The practice revealed a fatal flaw that nobody caught during peacetime testing. The propellant charge in American 76mm ammunition was based on a powder formulation designated M6. This was a single-base nitrocellulose powder that burned consistently and predictably under laboratory conditions. Under combat conditions, specifically the conditions found in Normandy during July and August of 1944, M6 powder behaved differently. Temperature affected burn rate. A propellant charge that generated 42,000 psi at 70 degrees Fahrenheit generated 38,000 psi at 40 degrees. Normandy's weather in summer 1944 was unusually cool and wet. Ammunition stored in sponson racks. Inside Sherman hulls maintained temperatures between 45 and 55 degrees, depending on outside conditions and how recently the tank had been running. That temperature differential cost approximately 400 feet per second in muzzle velocity. A round that should leave the barrel at 2,600 feet per second was actually traveling at 2,200. And penetration capability wasn't linear with velocity. The relationship followed a square function. Reduce velocity by 15%, and you lose roughly 28% of your penetration capability. Suddenly, a gun that should penetrate 4.2 inches of armor was barely managing 3 inches. Against a Panther's frontal armor, angled at 55 degrees from vertical, and presenting an effective thickness of 5.9 inches, 3 inches of penetration was completely inadequate. The rounds hit, deformed, and bounced off, leaving the Sherman crew exposed, and the Panther commander very much alive and angry. Briggs learned this from a tank commander who'd survived 3 separate engagements with Panthers. The lieutenant was 24 years old, looked 40, and spoke with the flat affect of someone who'd watched too many friends burn to death. He explained how his gunner would get solid hits at 300 yards, see the round impact dead center on the target's glacis plate, and watch it ricochet skyward while the Panther's 75mm gun rotated toward them with terrifying precision. The technical manual said it shouldn't happen. Combat said it happened every single day. Someone at the Ordnance Department knew about the temperature sensitivity issue because a classified bulletin dated June 15, 1944, recommended storing ammunition in heated compartments when possible. But Shermans didn't have heated ammunition storage. The bulletin was written by engineers who understood thermodynamics but apparently had never been inside a tank. Briggs stood in that maintenance depot with a problem that was killing American soldiers and an institution that moved too slowly to save them. Official solutions would require new propellant formulations, tested and qualified through channels involving chemists, ballistics experts, and procurement officers. That process would take months, maybe longer. The hedgerow fighting was happening now. He thought about the problem the way a welder thinks, in terms of heat, materials, and structural integrity under stress. If the propellant wasn't burning hot enough, you needed more heat in the system. You couldn't change the ammunition. That was manufactured in factories back in the States, shipped overseas in sealed containers, and issued to units through supply channels Briggs couldn't influence. But you could change the gun. Specifically, you could change how the gun retained and concentrated thermal energy during firing. The 76mm M1 gun tube was manufactured from forged steel, machined to precise tolerances, and designed to dissipate heat through air cooling between shots. That design philosophy made sense for sustained fire scenarios, where overheating was the primary concern. But what if you didn't want to dissipate heat? What if you wanted to trap it, concentrate it, and use accumulated thermal energy to boost the effective temperature of the propellant charge. The idea was either brilliant or insane, and Briggs wasn't entirely sure which. He knew that gun barrels were precision instruments with tolerances measured in thousandths of an inch. He knew that heating metal caused expansion, and expansion in the wrong places could destroy accuracy or even cause catastrophic failure. He also knew that German gun crews weren't worrying about technical manual specifications when they killed American tankers. He started with scrap metal from a destroyed Sherman, specifically sections of the hull armor that were still structurally sound despite combat damage. American Sherman armor was rolled homogeneous steel, not as hard as German face-hardened plate, but tough and ductile with good weldability. He cut strips approximately 2 inches wide and 12 inches long, using a cutting torch that wasn't officially authorized for this purpose. The plan was to create a thermal jacket around the breech end of the gun tube, the section where the propellant charge ignited and initial pressure built. By adding mass around the chamber area, he'd create a heat sink that absorbed thermal energy from firing and gradually raised the baseline temperature of the entire breech assembly. After 3 or 4 rounds, the accumulated heat would warm subsequent propellant charges through conduction, increasing their burn temperature and recovering some of the lost velocity. This violated at least 9 different Army technical orders. Gun tubes were sealed systems with specific thermal characteristics. Any modification to external dimensions could affect structural integrity, change resonant frequencies during firing, or create stress concentrations that led to catastrophic failure. The technical orders existed for legitimate reasons, written by engineers who understood metallurgy and structural mechanics better than any field welder. But those engineers weren't in Normandy watching Shermans burn. Briggs was. He began welding at 0300 hours, working alone in the maintenance bay with only a single work light and a clear understanding that if anyone caught him, his military career was over. The welding had to be perfect. Poor welds would create weak points where thermal stress could cause cracking. The jacket had to be symmetrically positioned to avoid creating uneven stress distribution, and the whole assembly had to maintain clearances for the gun's recoil mechanism. He used a 7018 electrode, low-hydrogen coating, designed for structural welding applications. Each pass had to penetrate fully, creating a complete fusion between the jacket strips and the existing gun tube surface. He worked slowly, methodically, letting each weld cool before starting the next to minimize heat accumulation that might warp the barrel. The finished modification added approximately 18 pounds to the gun tube, concentrated in a 12-inch section just forward of the breech. It looked crude, obviously non-standard, and would fail any official inspection immediately. It also might give American crews a fighting chance. At 0600 hours, Briggs had a thermal-jacketed 76mm gun ready for testing and no authorization to test it. He needed a tank crew willing to risk their lives on an unauthorized modification, a firing range where he could conduct tests without attracting official attention, and ammunition he could justify expending without requisition paperwork that would raise questions. What he found was Lieutenant James Morrison, the same tank commander who'd explained the penetration failures. Morrison looked at the modified gun, asked exactly 3 questions about structural integrity and safety, and said yes. Not because he trusted Briggs's engineering necessarily, but because the current situation was guaranteed to get him killed anyway, and at least this offered a chance. They conducted the first test firing at 0730, using a damaged Panther hull as a target at 300 yards. Morrison's crew loaded the first round, a standard M62 armor-piercing shot that under normal circumstances would bounce off the Panther's glacis plate. The gun fired with a sharp crack that sounded slightly different from a standard 76, a higher pitch that suggested different resonant properties. The round hit low, punched through the glacis plate, and exited through the rear armor, leaving a hole the size of a man's fist. Morrison's gunner stared through his sight, processing what he'd just seen, then turned to look at his commander with an expression somewhere between confusion and hope. They fired again. Same result. A third shot. this time at the turret ring where armor was thinner but angles were more severe. Penetration. Clean through. By the fifth shot, the gun tube was hot enough that you could feel the heat from 3 feet away, and the penetration performance was actually improving as the thermal jacket retained more energy. Briggs measured the barrel temperature with a contact pyrometer. After 5 shots, the breech section was running at 260 degrees Fahrenheit, hot enough that the propellant charges were being pre-warmed through conduction before firing. That pre-warming was recovering most of the lost velocity, boosting muzzle velocity back toward design specifications, and restoring penetration capability to what the technical manuals promised. The cost was barrel life. The added thermal stress would reduce the tube's service life from approximately 5,000 rounds to maybe 3,000, possibly less. But tank crews in Normandy weren't worried about whether their gun would last for 5,000 rounds. They were worried about surviving the next engagement. Morrison made a command decision that violated his orders, his commission, and probably several articles of the Uniform Code of Military Justice. He told Briggs to modify every 76mm gun in the battalion. By August 1st, 1944, Briggs had modified 17 76mm guns, working through the night shifts when officers were asleep and paperwork could be conveniently lost in the chaos of combat operations. The modifications weren't identical. Each gun had slightly different wear patterns, slightly different tolerances, and required custom fitting to ensure the thermal jacket didn't interfere with the recoil mechanism or breech operation. He developed a system. First, measure the gun tube's external diameter at 6 points along the breech section to identify any existing warping or wear. Second, cut the armor strips to match the specific gun's contours, allowing for thermal expansion. Third, tack weld the jacket in place and test fit the breech mechanism to ensure clearances were maintained. Finally, complete the welding using a specific sequence that minimized cumulative heat distortion. The entire process took approximately 4 hours per gun, assuming no complications. There were always complications. One gun had a hairline crack in the tube that wasn't visible until Briggs started welding, and thermal stress made it propagate. That gun had to be scrapped, and Briggs spent 3 hours explaining to a maintenance officer why they suddenly needed a replacement tube without admitting what he'd been doing. Another gun had an out-of-spec recoil mechanism that bound up when the thermal jacket changed the barrel's resonant frequency during firing. Briggs had to grind down sections of the jacket to restore proper clearances, destroying the symmetry. He'd carefully built and creating stress concentrations that would probably cause premature failure. But 15 of the 17 modified guns worked flawlessly, and those 15 guns were changing the tactical equation in ways that started attracting attention from people who asked dangerous questions. The first major engagement came on August 7th during the American breakout operation south of St. Lo. 2nd Armored Division pushed through German lines with 3 Sherman battalions, 2 equipped with standard 75mm guns and 1 with the new 76mm weapons. Intelligence reported German armor in the area, probably Panthers from the 2nd Panzer Division, but the Americans had numerical superiority and air support. What they didn't have was detailed information about German defensive positions in the bocage country, the nightmare landscape of narrow roads, high hedgerows, and small fields that turned every intersection into a potential ambush site. At 1400 hours, Company B ran straight into a prepared position held by 7 Panthers and supporting infantry. The engagement happened fast. Panthers opened fire from hull-down positions at 400 yards, their long 75mm guns trained on choke points where American tanks had to expose themselves crossing intersections. The first 2 Shermans, both mounting 75mm guns, died within 30 seconds. Penetrating hits through frontal armor, immediate catastrophic fires, no survivors. Lieutenant Morrison's platoon was 4th in the column. He had 4 tanks, 3 with standard 76mm guns, and his own with Briggs's thermal jacket modification. Standard doctrine called for immediate dispersal and flanking maneuvers, but the terrain didn't allow it. The hedgerows created natural corridors, and moving off the roads meant climbing earthen banks topped with vegetation so thick it would bog down a Sherman in seconds. Morrison made a decision that would either save his platoon or kill them all. Instead of retreating, he ordered his tanks forward, directly into the engagement zone, gambling that his modified gun would let him trade shots with Panthers on something approaching equal terms. His gunner, Staff Sergeant Thomas Chen, had been firing Shermans for 18 months and knew exactly how German armour behaved under fire. Panthers were nearly invulnerable from the front, but their side armour was only 40 millimeters thick, barely adequate against standard 75 millimeter rounds and completely vulnerable to a properly functioning 76. The problem was getting a side shot while German gunners were actively trying to kill you. Morrison's tank accelerated through the intersection, deliberately drawing fire while Chen traversed right, looking for angles. A Panther round hit their frontal armour at a slight deflection angle, penetrated the outer plate, and stopped against the inner, glacis, failing to fully penetrate but sending spalling fragments through the crew compartment. The driver took shrapnel in his left arm but maintained control. Morrison's loader caught fragments in his shoulder but kept loading. Chen ignored all of it, found his target, a Panther that had rotated slightly to engage another American tank, exposing perhaps 18 inches of side armour behind the turret. Chen fired. The round hit at the hull turret junction, penetrated, and detonated something inside the Panther that caused secondary explosions violent enough to blow the turret completely off the hull. German tankers called this effect brewing up, and it meant instant death for everyone inside. The other 3 Shermans in Morrison's platoon, equipped with standard 76 millimeter guns, engaged the remaining Panthers with mixed results. One achieved a mobility kill by destroying a Panther's track, immobilizing it but not killing the crew. Another fired 6 rounds at a hull-down Panther and achieved exactly 0 penetrations, every round bouncing off the angled frontal armour. Morrison's modified gun fired 9 rounds total during the 8-minute engagement. 4 complete misses, 2 penetrating hits on Panthers that achieved kills, 1 hit on a Panther that penetrated but failed to cause critical damage, and 2 hits on supporting vehicles that destroyed a half-track and disabled a truck. The Americans lost 4 tanks total. The Germans lost 2, Panthers confirmed, destroyed, 1 immobilized, and withdrew the remaining 4 rather than risk further losses. By the brutal mathematics of armoured warfare in Normandy, this counted as an American victory. Normally, engaging Panthers head-on resulted in American losses of 4 or 5 to 1. This engagement was nearly even. Word spread through the 2nd Armoured Division faster than official communications. Tank commanders compared notes and noticed that Morrison's platoon consistently achieved better results against German armour. Some attributed it to superior crew training or tactical skill, but the gunners talked among themselves, and gunners noticed things like unusual barrel configurations and the distinctive higher-pitched report of Morrison's main gun. By August 10th, Briggs was receiving unofficial visits from other battalion maintenance sections. Sergeants would appear after dark, ask careful questions about welding techniques and thermal properties, and leave with detailed measurements and sketches. The modification program was going viral through the armoured divisions, spreading through informal networks that bypassed official channels entirely. Division ordnance became aware something irregular was happening when requisitions for replacement gun tubes suddenly spiked. 76 millimeter barrels were rated for approximately 5,000 rounds of service life. Battalions were requesting replacements after 3,000 rounds, sometimes less. Someone filed a report, questioning whether American tubes were defective or whether field conditions were causing accelerated wear. That report landed on the desk of Colonel Herbert Watkins, Division Ordnance Officer, on August 15th. Watkins was a West Point graduate, career officer, and by-the-book administrator who believed regulations existed for good reasons, and deviations from specifications caused more problems than they solved. He ordered immediate inspections of all 76 millimeter guns in the division. The inspections revealed modifications on 43 weapons across 3 battalions, 43 unauthorized alterations to precision instruments, 43 violations of technical orders, and 43 potential courts-martial waiting to happen. Watkins was personally offended by this, not because he was rigid or bureaucratic by nature, but because he understood that field modifications bypassed safety testing that protected soldiers from catastrophic equipment failures. He'd seen what happened when poorly conceived modifications failed in combat. In North Africa, a maintenance sergeant had modified a 75mm gun's recoil mechanism to reduce firing signature, and the modified assembly failed during combat, sending the breech block backward through the turret with enough force to kill 2 crew members. That incident taught Watkins that good intentions weren't sufficient justification for unauthorized engineering. He convened a formal investigation on August 17th, summoning every maintenance officer whose section showed evidence of modifications. Briggs was identified as the source within 20 minutes of questioning. He was placed under arrest, confined to quarters, and informed he would face court-martial for destruction of government property, failure to obey technical directives, and conduct prejudicial to good order and discipline. Morrison, who'd been using the modified gun in combat, was also placed under investigation for knowingly operating non-standard equipment. 8 other officers received official reprimands for failing to identify and report unauthorized modifications in their units. The technical argument seemed straightforward from Watkins's perspective. The modifications increased thermal stress, reduced barrel life, created potential failure points, and operated outside the weapon's design parameters. That they appeared to work was irrelevant. Many dangerous practices work right up until they catastrophically fail and kill people. But while Watkins was building his case, something else was happening. Tank commanders were submitting combat reports that showed consistently improved performance from modified weapons. Kill ratios against German armor had improved from the disastrous 4-to-1 American losses to nearly even exchanges. Crew survival rates were up. Morale was improving because tankers believed they finally had weapons that gave them a chance. Major General Ernest Harmon, commanding 2nd Armored Division, read these reports with the perspective of a combat officer who measured success in battles won and soldiers alive, not technical compliance. He requested a demonstration, official testing of modified versus standard weapons under controlled conditions, with engineering staff present to evaluate safety. The demonstration occurred on August 23rd at a hastily established firing range using captured German armor as targets. Watkins attended with 2 ordnance engineers and a very unhappy expression. Briggs was temporarily released from arrest to explain his modifications and answer technical questions. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The test protocol was simple. Fire standard 76mm ammunition from both modified and unmodified guns at identical targets under identical conditions. Measure penetration, accuracy, and weapon reliability. Document any failures or safety issues. The standard gun performed exactly to specifications. At 300 yards, it penetrated 3.1 inches of vertical armor, consistent with technical manual predictions for ammunition at reduced temperature. At 400 yards, penetration dropped to 2.8 inches. Against a Panther glacis plate angled at 55 degrees, presenting effective thickness of 5.9 inches, the rounds bounced off completely. The modified gun, after 3 warm-up shots to bring the thermal jacket to operating temperature, penetrated 4.3 inches at 300 yards and 4 inches at 400 yards. Against the angled Panther armor, the first shot failed to penetrate, the second punched through, and the third went through so completely it exited the rear of the hull. Watkins watched this with visible frustration because the results contradicted his position, but didn't address his concerns about safety. He pointed out, correctly, that the test was conducted with new ammunition at optimal storage temperatures. Combat conditions involved ammunition stored in tanks for weeks, subjected to temperature variations, humidity, and the general chaos of field operations. He also noted that the modified gun's barrel showed measurable temperature increases that would, over extended firing, reduce service life significantly. His engineers calculated approximately 40% reduction in barrel longevity, which meant increased logistics burden and greater chance of in-combat failures. General Harmon listened to all of this, then asked a single question: which gun gives my tankers a better chance of killing Panthers before Panthers kill them? The answer was obvious, and Harmon made a command decision that prioritized combat effectiveness over maintenance schedules. He authorized the modifications as a provisional field expedient, pending formal evaluation by Army Ordnance Department. He ordered Watkins to establish quality control standards and inspection protocols to ensure modifications were done safely, and he quietly informed Briggs that his court-martial was cancelled, though his personnel file would note his tendency toward unauthorized initiative, which could be interpreted as either commendation or warning depending on who read it. The compromise satisfied no one completely but solved the immediate problem. Ordnance got oversight and safety standards. Combat units got weapons that worked. And Briggs got to return to modifying gun tubes, now with official approval and resources. The formal study conducted by Army Ordnance Department between September and November 1944 confirmed what field testing had shown. The thermal jacket increased effective chamber temperature by an average of 85 degrees Fahrenheit, recovering approximately 350 feet per second in muzzle velocity. Penetration capability increased by roughly 32% against face-hardened armor at combat ranges. The cost was accelerated barrel wear, increased maintenance requirements, and approximately 8% higher failure rate primarily due to stress cracks developing in the thermal jacket welds. But analysis of combat effectiveness showed that modified weapons achieved kills at 38% greater range and required fewer rounds per kill, offsetting the increased failure rate through improved first-shot effectiveness. By December 1944, the Army officially designated the modification as the M1A1E1 Field Expedient Kit, authorizing its use until improved ammunition with temperature-stable propellants could be fielded. That new ammunition, designated M93, began reaching units in March 1945, using a propellant formulation that maintained consistent burn rates across temperature ranges, from -20 to +120 degrees Fahrenheit. The M93 ammunition made the thermal jacket modifications obsolete from a performance standpoint, but the concept influenced post-war weapons development significantly. The principle that weapons should be optimized for actual combat conditions rather than ideal laboratory testing became embedded in Army procurement philosophy. Raymond Briggs survived the war. He participated in the drive across France, was present during the Battle of the Bulge in December 1944, and crossed into Germany with Third Army in March 1945. His personnel file shows 3 Bronze Stars for technical achievement under combat conditions, though the specific citations are vague about exactly what those achievements involved. The Army had learned that publicizing unauthorized modifications, even successful ones, created uncomfortable precedents. After VE Day in May 1945, Briggs was assigned to a technical evaluation team assessing captured German equipment. The irony wasn't lost on him. He spent months examining German tanks, guns, and engineering solutions, looking for innovations that could be adapted to American use. What he found surprised him in ways that contradicted popular narratives about German technical superiority. German equipment was often over-engineered, built to exacting standards that looked impressive on paper but created maintenance nightmares in field conditions. A Panther tank had a transmission so complex that replacing it required removing the entire front hull section, a 20-hour job that immobilized the vehicle completely. Sherman transmissions could be swapped in the field in under 4 hours. German guns were magnificent pieces of precision manufacturing that required specialized tools and factory-trained technicians to maintain. American guns were designed for maintenance by soldiers with basic mechanical training, using common hand tools. When Briggs examined a Tiger tank's 88mm gun, he found tolerances measured in microns, surface finishes, that required specialized grinding equipment and assembly procedures that allowed no improvisation. His thermal jacket modification would have been impossible on a German gun. The tolerances were too tight, the materials too specialized, and the entire philosophy too rigid. German engineering assumed perfect conditions, trained technicians, and adequate supply chains. American engineering assumed chaos, improvisation, and soldiers fixing things with whatever they could find. This wasn't a deficiency in American design. It was a deliberate philosophy that recognized war as fundamentally unpredictable and equipment as tools that had to work when everything else failed. The Sherman wasn't the best tank of World War II by any technical metric. It was the most practical tank, the one that could be built in enormous numbers, maintained by non-specialists, and adapted by field modifications when circumstances demanded. Briggs returned to Gary, Indiana in January 1946, collected his discharge papers, and went back to work as a pipe fitter. He married his pre-war girlfriend in March, had 3 children, and spent 32 years working in steel mills and manufacturing plants. He never spoke much about the war, which was common for that generation, and when he did mention it, he focused on his crew and the other maintenance personnel rather than his technical innovations. In 1968, a military historian researching Sherman tank modifications contacted Briggs for an interview. By then, he was 57 years old, working as a shift supervisor at a fabrication plant, and initially reluctant to discuss events from 24 years earlier. The historian persisted, and Briggs eventually agreed to a recorded interview that now resides in the Army Heritage and Education Center archives. The interview reveals a man who understood exactly what he'd done and why, but who remained uncomfortable with attention or praise. When asked if he'd been scared of court-martial, Briggs responded that he'd been more scared of watching tank crews die because their equipment didn't work. When asked if he considered himself an innovator, he said no, he considered himself a welder who'd seen a problem and tried to fix it using skills he already had. The historian pressed him on whether he believed field modifications should be encouraged or controlled, and Briggs gave an answer that reflected decades of thinking about the question. He said that modifications should be controlled because safety matters, but that control shouldn't mean prohibition. Soldiers in combat see problems that engineers in laboratories never encounter, and there needs to be a pathway for that knowledge to inform official solutions without requiring soldiers to choose between following regulations and surviving. That philosophy eventually became institutionalized in the American military's approach to equipment development. The process took decades and wasn't a straight line from Briggs's welding torch to formal policy, but the connection exists in traceable ways. In 1950, during the Korean War, American forces encountered Soviet T-3485 tanks that outmatched the M24 Chaffee light tanks initially deployed. The response involved rushing M4 A3E8 Shermans and M26 Pershing heavy tanks to Korea, but it also involved field modifications developed by maintenance units trying to improve performance under combat conditions. Tank crews added improvised armor, modified ammunition storage, and experimented with gun configurations that weren't in technical manuals. Army Ordnance, remembering the lessons from World War II, established formal field testing programs that evaluated these modifications systematically, rather than simply prohibiting them. Some modifications proved dangerous or ineffective and were banned, but others were validated and adopted as official field expedients. The M46 Patton tank, which entered service in Korea in 1951, incorporated design features directly influenced by field modification experience. Its ammunition storage included temperature-controlled compartments to address the propellant sensitivity issues that had plagued earlier weapons. Its gun mount allowed for easier barrel changes using common tools rather than specialized equipment. The entire design philosophy emphasized maintainability and field adaptability. By Vietnam, the Army had formalized the rapid fielding process, creating dedicated units that could evaluate field innovations, conduct safety testing, and implement approved modifications across the force within weeks rather than months or years. The Land Warfare Laboratory at Aberdeen Proving Ground established a direct liaison with combat units, collecting feedback about equipment performance and fast-tracking solutions to identified problems. This system wasn't perfect. Bureaucracy still moved slowly, and soldiers still found themselves using equipment that didn't quite match combat requirements. But the pathway from field observation to official solution had been established in ways that honored rather than punished innovation from soldiers who understood their equipment intimately. The technical legacy of Briggs's thermal jacket modification extended beyond the immediate World War II application. The principle that propellant temperature affects weapon performance became central to ammunition development programs. Modern tank ammunition uses temperature-stable propellants, specifically engineered to maintain consistent burn rates across extreme temperature ranges. The M829 armor-piercing, fin-stabilized discarding sabot round used in current M1 Abrams tanks performs identically, whether stored at -40 degrees or +140 degrees Fahrenheit. That capability didn't exist in 1944, and its development was directly motivated by combat reports documenting the temperature sensitivity problems that Briggs had, addressed through mechanical modification. Thermal management in weapon systems became a recognized engineering discipline. Modern tank guns include sophisticated cooling systems, thermal sleeves that insulate barrels from environmental temperature variations, and temperature sensors that provide real-time data to fire control computers. The M256 120mm smoothbore gun on the Abrams uses a thermal sleeve that maintains the barrel at consistent temperature regardless of ambient conditions, preventing the accuracy degradation that results from uneven thermal expansion. None of this would have prevented Briggs's specific problem in 1944, but all of it reflects an engineering philosophy that takes combat thermal environments seriously, rather than treating them as edge cases. That shift in thinking came directly from field experience documented by soldiers who modified equipment to survive. The broader question of innovation versus regulation remains unresolved and probably unresolvable. Military equipment must meet safety standards, must be standardized enough for logistics and training, and must be reliable enough that soldiers can trust it in life-threatening situations. But military equipment also operates in conditions that can't be fully predicted or simulated, and soldiers facing those conditions sometimes see solutions that engineers haven't imagined. The tension between these requirements produces the kind of situation Briggs found himself in. Regulations said, don't modify the gun, it's been tested and approved, and your changes might cause catastrophic failure. Combat said the approved gun doesn't work as promised, and American soldiers are dying because of it. Both positions were correct from their respective perspectives, and the resolution required judgment calls about acceptable risk that no technical manual could provide. Modern military doctrine attempts to balance this tension through formal rapid acquisition processes, embedded technical experts in combat units, and explicit policies about what modifications are permitted under field conditions. Soldiers can replace worn components, adjust settings within specified ranges, and implement approved field expedients without authorization. But they're prohibited from modifications that affect weapon structure, change mechanical timing, or alter pressure-bearing components without engineering review. These policies exist because of incidents like Briggs's modification, both the successes and the failures. For every field modification that worked brilliantly, there were others that failed catastrophically. The historical record documents improvised repairs that caused weapon explosions, modified ammunition that detonated prematurely, and creative solutions that killed the soldiers they were meant to protect. The Army learned, slowly and expensively, that the right answer isn't to prohibit all field modifications or to allow unlimited improvisation? The right answer is to create systems that evaluate modifications quickly, identify which innovations should be adopted broadly, and prevent dangerous practices from spreading, while still respecting the expertise of soldiers who live with the equipment daily. Raymond Briggs died in 1993 at the age of 72. His obituary in the Gary Post-Tribune mentioned his military service and his long career in manufacturing, but didn't mention the thermal jacket modification. Most people who knew him had no idea he'd influenced tank warfare doctrine or contributed to post-war weapons development. In 2007, a researcher working on a book about Sherman tank evolution discovered references to the thermal jacket program in declassified Army Ordnance documents. The researcher tracked down Briggs's 1968 interview, contacted his surviving family, and eventually published a detailed account of the modification program in the Journal of Military History. That article generated renewed interest in field modification programs during World War II, leading to several academic studies and eventually a Defense Department review of current policies regarding soldier-initiated improvements. The review concluded that while modern systems are more complex than World War II equipment, the principle remains valid. Soldiers who use equipment in combat conditions often identify performance issues and potential solutions before official testing reveals them. The M4A1 Sherman that Morrison commanded during the August 7th engagement, the tank equipped with the first combat-proven thermal jacket modification, survived the war. It fought through France, participated in the Battle of the Bulge, crossed the Rhine, and was present at the end of hostilities in May 1945. After the war, it was shipped back to the United States, used briefly as a training vehicle at Fort Knox, then transferred to the Ordnance Museum at Aberdeen Proving Ground. The gun tube with Briggs's modification was removed in 1946 during routine maintenance and should have been scrapped. Instead, a preservation-minded ordnance sergeant recognized its historical significance and stored it separately with documentation about its combat history. That tube remained in storage for 60 years before being rediscovered during a museum collection inventory in 2006. It now sits in the National Armor and Cavalry Museum at Fort Moore, Georgia, displayed alongside a standard 76mm tube for comparison. The placard describes the thermal jacket modification, explains the technical problem it addressed, and notes that it represents an example of soldier-initiated innovation that influenced modern weapons development. The display doesn't romanticize the story. It doesn't claim the modification won the war or revolutionized tank warfare. It presents the modification as what it was: a practical solution to a specific problem, developed by a skilled tradesman who understood materials and heat transfer, implemented by desperate tank crews who needed any advantage they could get, and eventually validated by an institution that learned to recognize innovation even when it arrived through unauthorized channels. That's perhaps the most important legacy, not the specific technical solution, which was obsolete within months, but the demonstration that soldiers closest to combat problems sometimes see solutions that engineers in laboratories don't, and that military institutions, despite their necessary emphasis on standardization and regulation, can learn to incorporate that knowledge rather than simply punishing deviation from approved procedures. The hedgerow fighting in Normandy during summer 1944 killed thousands of soldiers on both sides, destroyed hundreds of tanks, and tested equipment in ways no peacetime evaluation could replicate. American Sherman tanks faced German armor that was technically superior in nearly every measurable category, and American tankers found ways to fight and win anyway through better tactics, superior logistics, overwhelming numbers, and occasional technical innovations like Briggs's thermal jacket. The modification didn't change the fundamental reality that Shermans were outgunned by Panthers and Tigers. It didn't make American tanks invulnerable or even equal to their German counterparts. What it did was narrow the performance gap enough that superior American numbers, better crew training, and more reliable logistics could determine the outcome. It gave tank crews a fighting chance where before they'd had none, and in combat, a fighting chance is sometimes all you need. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe. March 19th, 1945, 31,000 feet above the Rhine Valley. Second Lieutenant Robert Harmon sits in the cramped cockpit of his P-47 Thunderbolt, scanning the sky through plexiglass already scratched by months of combat missions. His fighter group is escorting B-17 seconds, returning from Nuremberg when the radio crackles with urgent German voices, intercepted but not understood. Then he sees them. 8 Fokker-Wulf 190s diving from high altitude, positioning for a slashing attack on the bomber formation's vulnerable tail section. Harmon banks hard, pushing his throttle forward, but he knows the geometry is wrong. The German fighters will reach the bombers before his flight can intercept. He watches, helpless, as the 190s close to within 2,000 yards of the B-17 seconds. Then something impossible happens. The sky around the German fighters erupts in perfectly timed explosions. Not the familiar black puffs of conventional anti-aircraft fire arcing up from the ground far below, but bright, precise detonations occurring at exactly the altitude where the fighters are flying. One Fokker-Wulf disintegrates instantly. 2 others stagger, trailing smoke, and peel away from their attack run. The remaining German pilots scatter in confusion, their assault broken before they could fire a single round. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Harmon radios his wingman, asking if he saw anti-aircraft fire from the ground. Negative. The flak bursts appeared at bomber altitude, nowhere near the fighter's actual position moments before. Yet somehow, those explosions had found the German aircraft with uncanny precision. What Harmon witnessed was impossible according to everything 1945 aerial warfare doctrine taught. Anti-aircraft shells required direct hits or near misses to damage fast-moving fighters. Hitting a fighter moving at 400 miles per hour with a projectile fired from the ground was like shooting a bullet with another bullet. The statistical probability approached 0. Yet the German fighters had been hit, not by chance, not by volume of fire, but by shells that somehow knew exactly when to explode. This scene, repeated hundreds of times across European and Pacific skies during the final year of World War II, represented one of the most closely guarded secrets of the Allied arsenal. The proximity fuse, officially designated the VT fuse, was a miniaturized radar system small enough to fit inside an anti-aircraft shell, sophisticated enough to detect an aircraft and detonate the explosive charge at the optimal distance for maximum destruction. The technology was so revolutionary, so far ahead of anything Germany or Japan possessed, that its existence remained classified until after the war ended. German and Japanese pilots flew to their deaths, never understanding what killed them. Their commanders analyzed wreckage and battle reports but could not explain the impossible accuracy of American anti-aircraft fire. The truth was simple but devastating. American scientists had placed a complete radar system, including transmitter, receiver, amplifier, and triggering mechanism, inside a package small enough to fit in the nose of a 5-inch shell, robust enough to survive the 20,000 G-force acceleration of cannon launch, and reliable enough to function perfectly after being fired from a gun. The story of how this came to be, why it was developed with such desperate urgency, and why the Germans never discovered its secret even when it was literally falling from the sky into their hands, reveals one of the most fascinating technological races of World War II. The development began not with American innovation, but with British desperation. By late 1940, Britain faced an existential crisis. The Luftwaffe's bombing campaign, the Blitz, was destroying British cities night after night. Between September 7th, 1940 and May 11th, 1941, German bombers killed more than 43,000 British civilians and wounded another 139,000. London alone endured 57 consecutive nights of bombing. Anti-aircraft defences, the primary means of defending against aerial attack, were proving catastrophically ineffective. British 3.7-inch anti-aircraft guns fired time-fused shells, projectiles with mechanical clockwork fuses set before firing to explode at a predetermined altitude. The gun crew would estimate the target aircraft's altitude, calculate the required fuse timing, set the fuse mechanism, load the shell, and fire. If their calculations were correct, the shell would explode near the aircraft. If their calculations were wrong, the shell exploded harmlessly in empty sky or failed to explode at all. The accuracy requirements were brutal. A bomber, flying at 15,000 feet and 300 miles per hour, covered 440 feet every second. The anti-aircraft shell took approximately 10 seconds to reach 15,000 feet. During those 10 seconds, the aircraft moved 4,400 feet, nearly a mile. Gun crews had to estimate not where the aircraft was, but where it would be 10 seconds in the future, accounting for altitude changes, course changes, and speed variations. They had to set mechanical fuses accurate to fractions of a second. Then they had to fire the gun with precise timing. Any error in estimation, fuse setting, or firing timing meant a complete miss. Statistics from 1940 revealed the grim reality. British anti-aircraft guns required an average of 20,000 rounds fired to achieve one aircraft destroyed. 20,000 shells to bring down one bomber. Each 3.7-inch shell cost approximately £3 to manufacture. Destroying a single German bomber cost British taxpayers £60,000 in ammunition alone, not counting the wear on gun barrels, the labour of gun crews, or the cost of the guns themselves. Worse still, those 20,000 rounds represented enormous industrial capacity. Britain's factories, already struggling to produce enough tanks, ships, aircraft, and ammunition for a global war, were diverting precious resources to manufacture shells that missed their targets 99.995% of the time. The problem was not incompetent gun crews. British anti-aircraft gunners were highly trained, many with months of intensive practice. The problem was physics and mathematics. Hitting a moving target at 15,000 feet with a time-fused shell required solving a three-dimensional calculus problem in real time under combat conditions, while the target actively maneuvered to avoid being hit. Human beings, even highly trained ones, simply could not perform these calculations with sufficient accuracy. Mechanical gun directors, sophisticated analog computers that British and American forces deployed throughout the war, improved accuracy but could not overcome fundamental limitations. These devices could calculate future target positions based on current observations, but they could not account for target maneuvering. A bomber that suddenly changed altitude or course after the shell was fired would evade the predicted interception point. What British air defence desperately needed was a shell that could adjust its detonation point after being fired, a projectile that could sense when it was near an aircraft and explode automatically at the optimal moment for maximum damage. This concept, a proximity fuse, had been theoretically discussed for years. The idea was simple. Place a sensor inside the shell that could detect an aircraft. Connect the sensor to a triggering mechanism that would detonate the explosive charge when the sensor detected the target. It was extraordinarily complex. Any sensor system had to survive being fired from a gun. Anti-aircraft guns generated accelerations exceeding 20,000 times the force of gravity during firing. This acceleration was sufficient to shatter glass, deform metal, and destroy virtually any electronic component. The sensor system had to function in a projectile spinning at hundreds of revolutions per second, subjected to aerodynamic forces that would tear apart improperly designed components. It had to operate reliably at altitudes up to 30,000 feet, where temperatures dropped to -40 degrees Fahrenheit and atmospheric pressure fell to 1/3 of sea level. It had to function despite the electrical noise generated by the shell's own passage through the air, despite condensation and humidity, despite the violent shock of gun launch. And it had to be manufactured cheaply enough for mass production. A proximity fuse that cost more than the shell itself would be economically impractical. Multiple approaches were theoretically possible. An acoustic fuse could listen for the sound of aircraft engines. A photoelectric fuse could detect changes in light levels as the shell passed near an aircraft's shadow. A magnetic fuse could sense the iron content of aircraft structures. Each approach had fatal flaws. Acoustic sensors could not distinguish aircraft engine noise from the shell's own supersonic passage through air. Photoelectric sensors required line of sight to the target and failed in clouds or darkness. Magnetic sensors had insufficient range, requiring the shell to pass within a few feet of the aircraft to trigger. The solution, proposed independently by British and American researchers, was radar. A miniature radar system in the shell's nose could transmit radio waves and detect their reflection from nearby aircraft. When the reflected signal reached sufficient strength, indicating the shell was near the target, the fuse would trigger detonation. The concept was elegant. The engineering challenges were immense. Radar systems in 1940 were massive installations. The British chain-home radar stations that detected Luftwaffe raids during the Battle of Britain used transmitters the size of buildings, antennas mounted on 350-foot towers, and receivers requiring truck-mounted equipment. The proposed proximity fuse needed to compress this technology into a package 5 inches in diameter and 8 inches long, weighing less than 4 pounds. In Britain, the Telecommunications Research Establishment began exploring proximity fuse designs in 1940. The research team, led by physicists who had pioneered British radar development, quickly realized the magnitude of the challenge. Vacuum tubes, the electronic components essential for radio transmission and reception, were fragile glass devices. Subjecting them to 20,000 G acceleration would shatter them instantly. The team experimented with ruggedized vacuum tube designs, reinforcing the glass envelopes and modifying internal structures to withstand shock. Progress was slow and frustrating. By mid-1940, German bombing had forced the TRE to relocate from its original location to a safer site in Dorset. Research continued, but resources were limited. Britain's industrial capacity was fully committed to immediate war production. Developing an experimental fuse, no matter how promising, competed with urgent needs for aircraft, tanks, and ships. The breakthrough would come from across the Atlantic, where American industrial capacity and scientific talent would transform the proximity fuse from theoretical concept to war-winning weapon. In June 1940, before the United States entered the war, President Roosevelt authorized the TIZAD mission, a delegation of British scientists who would travel to America to share Britain's most closely guarded military secrets. The mission, led by Sir Henry Tizard, carried with it details of British radar technology, jet engine designs, explosive research, and proximity fuse concepts. The objective was to engage American industrial and scientific capacity in developing technologies Britain could not produce in sufficient quantity alone. Among the American scientists who received these briefings was Merle Tuve, director of the Department of Terrestrial Magnetism at the Carnegie Institution in Washington. Tuve, a brilliant experimental physicist, immediately grasped the proximity fuse's potential. He also understood that developing it would require unprecedented coordination between academic researchers, industrial manufacturers, and military services. Tuve became the driving force behind American proximity fuse development. In September 1940, he convinced the National Defense Research Committee to establish a dedicated fuse development program. The program, designated Section T, brought together physicists, engineers, and technicians from universities, private industry, and government laboratories. The team's first task was to solve the vacuum tube problem. Standard radio tubes could not survive gun launch. The team needed tubes specifically designed to withstand extreme acceleration. This required rethinking vacuum tube construction from first principles. Traditional tubes used relatively delicate internal structures, thin wires supporting electrodes within evacuated glass envelopes. These structures flexed and broke under high acceleration. The solution was to make everything smaller, thicker, and stronger. Engineers designed new tubes with massive electrodes, thick support wires, and reinforced glass envelopes. The tubes were tiny, barely larger than a thimble, but incredibly robust. Testing involved firing prototype tubes from guns and examining survivors. Early designs failed catastrophically. Glass shattered. Internal elements broke loose. Vacuum seals failed. The team systematically identified failure modes and redesigned the components. By early 1941, they had developed vacuum tubes that consistently survived 20,000 G acceleration. These tubes, designated the 6AK5 and related designs, represented a revolutionary advance in rugged electronics. But surviving gun launch was only the first challenge. The tubes had to function in a complete radar system. The fuse needed a radio transmitter to send out radar signals, a receiver to detect reflections, an amplifier to boost the weak reflected signals, and a triggering circuit to detonate the explosive charge when the reflected signal reached threshold intensity. All of this had to fit inside the shell's nose cone, operate on battery power, function reliably despite spin and vibration, and cost less than $50 per unit for mass production. The engineering team divided the problem into subsystems. One group worked on the radio frequency oscillator that would generate the radar signal. Another developed the receiving antenna and detector circuit. A third group designed the amplifier stages. A fourth worked on the triggering mechanism that would actually fire the explosive charge. Each subsystem presented unique challenges. The radio frequency oscillator had to generate a stable signal at approximately 200 MHz, a frequency high enough to reflect efficiently from aircraft structures, but low enough that available vacuum tubes could generate sufficient power. The antenna had to be omnidirectional, since the spinning shell would constantly change orientation relative to the target. The detector circuit had to distinguish genuine aircraft reflections from ground reflections, rain, clouds, and electronic noise. By mid-1941, Section T had developed a working prototype. The fuse, designated T3, was tested at the U.S. Naval Proving Ground at Dahlgren, Virginia. On August 19, 1941, a 5-inch anti-aircraft shell, fitted with a T3 fuse, was fired at a radio-controlled target drone flying at 10,000 feet. The shell exploded 60 feet from the drone, close enough that shrapnel severely damaged the aircraft. The test was successful beyond expectations. For the first time in history, an anti-aircraft shell had detected its own target and detonated itself at the optimal moment. The implications were staggering. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The successful test triggered immediate expansion of the Proximity Fuse program, the U.S. Navy, recognizing the technology's potential for defending ships against aircraft attack, became the primary sponsor. The Navy designated the fuse, the VT fuse, officially standing for variable time to disguise its true nature, though researchers joked it meant vacuum tube. Production planning began immediately. The fuse's complexity meant traditional ammunition manufacturers lacked the necessary expertise. Section T partnered with electronics companies, radio manufacturers, and companies with experience in miniature devices. The Eastman Kodak Company, with expertise in precision mechanics and mass production, became a primary contractor. Western Electric, Sylvania, and other electronics firms contributed specialized components. By December 1941, when Japan attacked Pearl Harbor and Germany declared war on the United States, the Proximity Fuse program was already well advanced. America's entry into the war transformed the program's urgency. The Navy needed proximity fuses immediately for defending ships against Japanese air attack. The fuse design was refined for reliability and manufacturability. Engineers simplified circuits, standardized components, and developed quality control procedures. By mid-1942, production had begun. Initial fuses cost approximately $70 each, expensive but acceptable given their effectiveness. As production volumes increased, costs dropped steadily. By 1944, mass production techniques reduced the price to approximately $20 per fuse, making them economically viable for widespread use. The fuse's effectiveness exceeded all predictions. Tests against maneuvering aerial targets showed that shells with proximity fuses were approximately 5 times more likely to destroy an aircraft than shells with time fuses. This translated directly into ammunition savings. If a time-fuzzed shell required an average of 20,000 rounds per kill, a proximity-fuzzed shell needed only 4,000 rounds. The difference was more than statistical. It was the difference between effective and ineffective air defense. 5-fold improvement in kill probability meant that a naval vessel under air attack could destroy incoming aircraft with 1/5 the ammunition expenditure. Ships could defend themselves effectively rather than simply filling the sky with shells and hoping for lucky hits. For the American Navy fighting across the vast Pacific, this capability was transformational. The first combat use of proximity fuses came in January 1943 during the naval battle of Rennell Island in the Solomon Islands. American cruisers, equipped with 5-inch guns, firing proximity-fused shells, engaged attacking Japanese torpedo bombers. The results stunned observers. Japanese aircraft, accustomed to pressing attacks through anti-aircraft fire, were blown from the sky with shocking efficiency. Pilots who survived reported explosions erupting around their aircraft with uncanny accuracy, shells that seemed to know exactly where they were. The Japanese Navy recognized that American anti-aircraft fire had suddenly become far more deadly, but they could not determine why. Captured proximity fuses, recovered from shells that failed to detonate, were examined by Japanese scientists. The shells appeared to contain standard explosive charges. The fuse mechanism in the nose was damaged beyond recognition by impact. Japanese analysts concluded the Americans had developed improved time fuses with better mechanical clockwork, not realizing they were examining the shattered remains of miniature radar systems. This misunderstanding was deliberate. American forces were under strict orders regarding proximity fuse security. The fuses could only be used over water where unexploded shells would sink rather than fall into enemy hands intact. They could not be used over land where the enemy might recover working examples. Shells that failed to detonate over water would sink into hundreds of fathoms, making recovery impossible. These security restrictions remained in force throughout 1943 and into 1944. The fuses proved devastatingly effective against Japanese air attacks but remained a closely guarded secret. The restrictions frustrated army commanders who desperately wanted proximity fuses for defending ground forces against air attack. General George Marshall personally appealed to Navy leadership for permission to use proximity fuses in ground operations, arguing that the technology could save thousands of American lives. The Navy and the National Defense Research Committee remained adamant. The risk of compromising the fuse's secret was too great. The restrictions would finally lift in December 1944 during the Battle of the Bulge. Germany's surprise offensive through the Ardennes caught Allied forces off guard. German aircraft, appearing in strength for the first time in months, attacked American positions with relative impunity. Weather conditions grounded Allied fighters. German ground forces pushed American units back, threatening to break through Allied lines and reach the strategic port of Antwerp. The situation was desperate enough that General Dwight Eisenhower, Supreme Commander of Allied forces in Europe, authorized the use of proximity fuses by anti-aircraft units defending against German air attacks. The restriction against overland use was lifted. For the first time, proximity-fused shells would be fired where the enemy could potentially recover unexploded examples. The first large-scale use came on Christmas Eve, 1944. The Luftwaffe launched Operation Bodenplatte, a massive air offensive intended to destroy Allied aircraft on the ground and gain temporary air superiority. More than 1,000 German fighters and bombers attacked Allied airfields across Belgium and France. American anti-aircraft batteries, equipped with proximity-fused shells, met the attacking aircraft with withering fire. The results exceeded even optimistic predictions. German aircraft fell from the sky in unprecedented numbers. Luftwaffe pilots, veterans of years of combat, reported in shock that American anti-aircraft fire had become impossibly accurate. Shells exploded directly alongside aircraft with no apparent aiming error. Entire formations were torn apart by flak that seemed to track individual aircraft. The German High Command received urgent reports describing the mysterious new American ammunition. Pilots reported shells that exploded without apparent reason, creating perfectly timed airbursts that required no direct hits. Intelligence officers analyzed the reports but could not explain the phenomenon. The conclusion seemed impossible. The Americans had developed some form of guided ammunition, but how could an artillery shell, fired from a ground-based gun, possibly guide itself toward a target? German scientists examining the problem quickly dismissed the idea of guidance. The forces involved in gun launch would destroy any guidance mechanism. The spin rates would make control impossible. Whatever the Americans had developed, it could not be a guided projectile. Some analysts suggested improved mechanical time fuses. Perhaps the Americans had developed clockwork mechanisms of extraordinary precision. Others proposed that American gun directors, the analog computers that calculated firing solutions, had been improved to the point where their time fuse settings were simply more accurate. A few analysts suggested the possibility of proximity detection, shells that could somehow sense when they were near an aircraft and detonate automatically. But this seemed equally impossible. What sensor could survive gun launch? How would it be powered? How could it function reliably in combat conditions? The truth was too far beyond German expectations to be considered seriously. The Germans had their own proximity fuse research program, but it had focused on magnetic and acoustic sensors. These approaches had proven impractical. German scientists had concluded that proximity fuses were theoretically interesting but practically impossible with current technology. They assumed American scientists had reached the same conclusion. This assumption proved fatal. By early 1945, proximity fuses were standard ammunition for American anti-aircraft units in Europe. The effects were measurable and devastating. German air activity declined sharply. Luftwaffe pilots who survived encounters with proximity-fused anti-aircraft fire reported their experiences to their commanders, describing the impossibly accurate flak that made daylight operations suicidal. Night operations became marginally safer, but even at night, proximity fuses functioned effectively. The radar detection range of the fuses was approximately 100 to 150 feet, sufficient that shells passing anywhere near an aircraft would detonate. For fast-moving fighters flying at 300 to 400 miles per hour, this detection range meant shells had to pass only marginally close to achieve kills. The pilots had perhaps 1/10 of a second to recognize that a shell was approaching and attempt evasive maneuvers. By the time they saw the shell or its smoke trail, detonation was already occurring. Statistical analysis from early 1945 demonstrated the proximity fuse's devastating effectiveness. In January 1945, American anti-aircraft units in Europe reported destroying German aircraft at a rate 5 times higher than the previous year, despite firing fewer total rounds. The ammunition savings were enormous. Proximity fuses effectively quintupled the combat power of every anti-aircraft battery, allowing fewer guns to defend larger areas with greater effectiveness. The technology's impact extended beyond air defense. In December 1944, American artillery units discovered that proximity fuses transformed conventional artillery into devastating anti-personnel weapons. Artillery shells fitted with proximity fuses could be set to detonate at optimal heights above ground, creating airbursts that showered shrapnel downward over wide areas. Unlike contact-fused shells that buried themselves in mud before exploding, or time-fused shells that required precise calculation, proximity-fused shells automatically detonated at the most lethal height. German infantry advancing through the Ardennes during the Battle of the Bulge encountered this new horror. American artillery shells exploded 20 to 30 feet above ground, exactly the height that maximized casualties among troops in the open or in foxholes. The psychological impact was profound. German soldiers had learned to take cover when artillery fire began, knowing that shells needed direct hits or very close misses to cause casualties. Proximity-fused shells eliminated that safety margin. There was no safe place on the battlefield when American artillery fired. Major General James Gavin, commanding the 82nd Airborne Division during the Battle of the Bulge, later described proximity fuses as decisive in stopping German advances. His paratroopers, outnumbered and outgunned, held critical positions because supporting artillery could deliver devastating fire with unprecedented efficiency. German attacks that should have overrun American positions were shattered by perfectly timed airbursts. Gavin estimated that proximity fuses increased artillery effectiveness by a factor of 3 to 4. A single artillery battalion firing proximity-fused shells could deliver the firepower of 3 battalions firing conventional ammunition. This multiplication of combat power came at a moment when American forces were desperately outnumbered and outmaneuvered. German attempts to understand and counter proximity fuses continued through the war's final months. In January 1945, German forces recovered several unexploded proximity-fused shells from Belgian battlefields. These shells, their fuses intact, were rushed to German research facilities for examination. What German scientists discovered shocked them. The fuses contained complete miniature radar systems, technology Germany had not believed possible to miniaturize to such degree. The vacuum tubes were unlike anything in German production, designed specifically to survive gun launch. The circuits were ingeniously simple yet effective. The entire assembly represented a level of miniaturization and ruggedization that German electronics industry could not duplicate. German engineers examining the fuses realized that even if they understood the principles, Germany lacked the industrial capacity to manufacture proximity fuses in meaningful quantities. The specialized vacuum tubes required production techniques Germany had not developed. The precision assembly demanded skilled labor in quantities Germany could not spare. The raw materials, particularly the exotic metals used in vacuum tube construction, were unavailable. Most critically, Germany no longer had time. By February 1945, Allied forces were advancing into Germany from both east and west. German industrial capacity was collapsing under sustained bombing. Even if German scientists had developed proximity fuse designs, there was no possibility of production before Germany's inevitable defeat. The irony was that Germany possessed the basic scientific knowledge necessary for proximity fuse development. German physicists understood radar principles thoroughly. German engineers had pioneered many aspects of radio technology. What Germany lacked was the industrial infrastructure for mass production of complex electronic devices and the secure time necessary for development and testing. America's geographic isolation from the war's fighting fronts provided American scientists and engineers with 3 years of relatively undisturbed research and development. American factories, safe from bombing, could tool up for mass production. American supply chains, protected by oceans and Allied naval power, could deliver specialized materials. This combination of scientific capability, industrial capacity, and strategic security created the conditions for technological breakthroughs. Germany could not match. By war's end in May 1945, American industry had manufactured more than 22 million proximity fuses. This staggering production volume transformed a revolutionary technology into standard ammunition. 5-inch naval shells, 90mm anti-aircraft shells, 105mm artillery shells, all could be fitted with proximity fuses. The technology that had begun as a desperate solution to British air defense problems had become routine equipment for American forces. The human cost of this technology to German and Japanese forces was severe, but difficult to calculate precisely. Conservative estimates suggest proximity fuses were responsible for destroying or damaging several thousand aircraft that would have survived conventional anti-aircraft fire. Each aircraft represented a trained pilot, months of training, scarce resources diverted from other uses. More significantly, the psychological impact of facing impossibly accurate anti-aircraft fire degraded enemy willingness to press attacks. Japanese kamikaze pilots, who had shown willingness to fly into ships despite intense anti-aircraft fire, found proximity fuzzes changed the calculus. Previously, a kamikaze pilot could hope that American gunners would miss or that he could maneuver through the fire. Proximity fuses eliminated that hope. The shells would find him regardless. American naval gunners reported that kamikaze attacks in 1945, when all ships carried proximity-fused ammunition, were less aggressive and less successful than earlier attacks. Pilots seemed to abandon their dives at greater distances, flinching from the accurate fire they could not evade. The proximity fuse's development represented one of the most successful scientific mobilization efforts of World War II. From initial concept in 1940 to mass production by 1943 required just 3 years. This pace of development demonstrated what could be achieved when scientific genius, industrial capacity, and military necessity aligned. The program cost approximately $27 million, a substantial sum but trivial compared to the technology's impact. Those $27 million purchased a weapon system that multiplied American anti-aircraft and artillery effectiveness by factors of 3 to 5. In economic terms, proximity fuses represented one of the highest return on investment weapons systems of the entire war. The technology's influence extended far beyond World War II. Proximity fuses established principles that guided post-war weapons development. The concept of smart ammunition, projectiles that could sense their environment and adjust their behavior accordingly, became central to modern military technology. Today's guided missiles use radar, infrared, and laser sensors to detect and track targets. Modern artillery shells contain GPS receivers and guidance systems. Anti-aircraft missiles use sophisticated seekers that can distinguish between targets and decoys. All of these technologies trace their lineage directly to the World War II proximity fuse. The engineering challenges overcome in developing the proximity fuse, particularly the creation of electronics that could survive extreme acceleration and operate reliably in hostile environments, influenced civilian technology development. The ruggedized vacuum tubes developed for proximity fuses found post-war applications in portable radios, test equipment, and early computers. The miniaturization techniques pioneered for fuse production contributed to the broader trend towards smaller, more reliable electronic devices. Security surrounding proximity fuses remained tight even after the war ended. The technology was not declassified until 1946, more than a year after Germany's surrender. American military authorities wanted to preserve the advantage proximity fuses provided. The Cold War was beginning, and proximity fuses represented a significant American technological edge over potential adversaries. Only after the Soviet Union demonstrated its own proximity fuse designs did the United States relax classification restrictions. Even then, many technical details remained classified for years. The full story of proximity fuse development, including the contributions of individual scientists and engineers, only became public in the 1950s and 60s as participants published memoirs and technical histories. Today, examples of World War II proximity fuses are preserved in military museums. They appear unremarkable, small cylindrical devices that could fit in a hand, yet these simple-looking objects represented revolutionary technology that changed warfare. The miniature radar systems they contained, primitive by modern standards, were sophisticated enough to detect aircraft at ranges sufficient for effective anti-aircraft fire. The ruggedized vacuum tubes, engineered to survive, and forces that would destroy conventional electronics, demonstrated that careful design could overcome apparently insurmountable limitations. The production techniques that allowed mass manufacture of complex electronic devices established precedents for the modern electronics industry. For the German pilots who survived encounters with proximity-fused anti-aircraft fire, the experience remained vivid decades later. Former Luftwaffe pilots interviewed in the 1970s and 80s spoke with residual shock about the sudden transformation of American anti-aircraft fire in late 1944. They described flying through flak that seemed to track individual aircraft, shells that exploded with uncanny precision. Several veterans stated they had assumed American gun crews had achieved superhuman levels of skill. The idea that the shells themselves contained guidance systems had not occurred to them during the war, learning decades later that they had faced miniature, radar-guided weapons explained experiences that had seemed incomprehensible at the time. The proximity fuse story demonstrates how technological innovation can shift military balance decisively. Germany entered World War II with technological advantages in tanks, aircraft, and tactical doctrine. The United States overcame these advantages not through superior courage or greater numbers, though both played roles, but through sustained technological innovation. Proximity fuzzes represented one element of a broader pattern. American scientists and engineers, given adequate resources and clear objectives, developed weapons systems that German industry could not match. The atomic bomb represents the most dramatic example, but proximity fuses, radar, long-range bombers, and advanced fighters all contributed to American technological superiority that proved decisive in the war's final years. The human element of the proximity fuse story deserves emphasis. Behind the statistics and technical details were thousands of individuals whose contributions enabled the technology's success. Scientists like Merle Tuve, who recognized the fuse's potential and drove development forward. Engineers who solved seemingly impossible technical challenges. Factory workers who manufactured millions of complex devices with the precision necessary for reliable operation. Military personnel who tested prototypes under combat conditions and provided feedback that guided improvements. The proximity fuse succeeded because talented, dedicated people worked toward a common goal with clear understanding of the stakes. For Second Lieutenant Robert Harmon, the P-47 pilot who witnessed proximity phases destroy German fighters in March 1945, the technology remained mysterious until after the war. He completed his combat tour, returned to the United States, and only learned about proximity fuses years later, when declassification allowed publication of their history. Reading about the technology, he finally understood what he had witnessed that day above the Rhine Valley. The impossibly accurate flak that had saved the bomber formation had been the work not of superhuman gunners, but of miniature radar systems guiding each shell to its target. The knowledge did not diminish his respect for the achievement. If anything, understanding the engineering brilliance behind proximity fuses increased his appreciation for the men who had developed and manufactured them. The legacy of the proximity fuse extends into the present day. Every time a modern military aircraft deploys countermeasures against an incoming missile, the pilot benefits from lessons learned developing World War II proximity fuses. Every time an artillery battery fires precision-guided shells, the gunners use technology descended from those early radar-fused projectiles. The fundamental concept that projectiles can sense their environment and adjust their behavior accordingly has become central to modern warfare. What seemed revolutionary in 1941 is now routine. This transformation, from impossible to routine in less than a century, demonstrates humanity's capacity for rapid technological advancement when necessity demands and resources allow. The story of the proximity fuse is ultimately about the transformation of warfare through applied science. In 1940, hitting an aircraft with anti-aircraft fire required 20,000 shells and extraordinary luck. By 1945, the same task required 4,000 shells and a proximity fuse. This five-fold improvement in effectiveness came not from better aim or more powerful guns, but from placing intelligence into the projectile itself. The shell could sense its target, judge the optimal moment for detonation, and execute that decision in fractions of a second. This represented a fundamental shift in weapons technology, from purely mechanical systems to electromechanical systems that could respond to their environment. Modern warfare has continued this evolution, with weapons systems that can identify targets, plan approaches, and execute attacks with minimal human intervention. The proximity fuse marked an early step in this ongoing transformation. For the thousands of Allied airmen who survived the war because proximity fuses protected them, the technology was quite literally life-saving. Every bomber that returned safely because German fighters were driven off by accurate anti-aircraft fire, every ship that survived kamikaze attacks because proximity-fused shells destroyed incoming aircraft, every soldier who lived through the Battle of the Bulge because American artillery delivered devastating fire support, all of these outcomes resulted from one technology developed in response to a clear need. The proximity fuse did not win World War II alone. No single technology could claim that distinction, but it contributed measurably to Allied victory and reduced casualties that would otherwise have been far higher. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.